Let's start. Okay, welcome to the department seminar. So our seminar speaker today is Professor Cheng-Ta Chen from National Taiwan Normal University. Professor Chen obtained a PhD in atmospherical and ocean science from Princeton University, and after that he went to Max Planck for a postdoc, and he is now a distinguished professor at the National Taiwan Normal University. And Professor Chen's research expertise focused on cloud radiation and climate modeling. And in recent years, he became to focus on this extreme weather and climate event. And recently, he developing a way to identify extreme event in a different way that not most of people use that way. So I feel that's a very interesting new method to detect this extreme event, because it helps us to find out what is the physical mechanism behind the extreme event. So today, he will be telling us applying this method, particularly for North America. So, Cheng-Ta,
Okay.
please.
Thank you for the introduction. Yeah, it's very nice to have this opportunity to present some of our recent study on how the extreme heat wave change in the past over North American regions, in how the projected change from those CMAP6 models. But another purpose, as Professor you mentioned, that I try to promote methodology that we use to track, detect and track this weather and climate extreme from an event perspective as an alternative, to provide an alternative view to a more traditional studies on using extreme indices typically. So I will start with some background and motivation, and then the data we use, and introduce the methodology we have on this detection tracking. Then after we we apply to the data set, and you can get the whole heat wave event archive in the history. And then you can sort of rank the top events if you like. And then also you can take a statistic of how this event and their attribute change in the past, and also apply to the CMAP6 models to try to look at future change, or try to maybe first test the reliability of a model to simulate this heat wave from an event perspective, and then look at the future change. And I will conclude in the end and talk about some of the future work and possibilities. Okay. So if you look at the disaster record in the international disaster database, like this EMDAT data set, that certainly you'll find that heat wave has a large impact on mortality, especially for these elderly peoples. And actually, if you even look at the US, that actually more people in US that have died from heat wave than flooding, tornado, hurricane, and lightning combined together. So this is why people are sort of keen in learning about how this heat wave extreme will change. And the same, if you look at the European region, look at both their common data set and the data set from this reinsurance company, that almost more than 85% of the fatality associated with nature disaster are due to heat wave. Okay. And for disaster record, both, as I said, government agency and reinsurance company does count the event numbers instead of more traditionally, when people working on this climate analysis on the extreme, they typically use only this, use some sort of defined extreme indices and apply to a specific station a grid point or a average of a selected area, if you like. And for example, here is one of the EPA study on this heat wave characteristic in 50 major US cities from 1961. And for example, for the heat wave frequency, that they used to be only 2 per year in 1960, and now it's every year you can have a 6 heat wave, for example. Or duration used to be 3 days on average in 1960, and now it's 4 days, 1 day more in general after 2000. Okay. And also intensity increase in these cities as well. Or when people working on a climate model, they even use this specific weather and climate extreme indices from this expert team of WCRP. For example, here is sort of a warm spare duration index as long as this particular temperature reach some high certain tile like 90, 95% for several days, then you count it as an occurrence of a heat wave. And then you typically count how many days will increase, and for the heat wave, definitely the number of days for the heat wave from current climate, if you look even the mid-century, it increased quite a bit. But what exactly is the difference when I say extreme event and extreme indices? That's why we described earlier, if you look at a publication in the literature, that most of the climate extreme study are using extreme indices. For example, this on the right-hand side here from IPCC report, which typically uses the so-called annual maximum temperature. So 1 year, take one, and then you use that with some of this extreme value statistic. You can derive the 50-year event in terms of return level or return period, for example. So here, typically in IPCC say that in 19th century, for those events that occur every 50 years, after 4-degree global warming level, then it's pretty much occur every year. And when they occur, the intensity or the temperature during those events are increased more than 5 degrees. So those are typical things you see. But for most of the general public, what they think about extreme event, certainly most those cause a lot of damages and losses. So it's the things that they remember. For example, I can use this 2021 summer Pacific Northwest heat wave as an example. So people know that because, well, it's showing that in media report all the time, and also the meteorologists in the TV station talking about those events, heat wave and so on. Okay, so it's typical.
Which is baking the Pacific Northwest. Nearly 20 million people are under an excessive heat warning this morning, covering nearly all of Washington and Oregon, plus 5 other states. Lilia Luciano has more.
It's never been hotter across the Northwest. A record 112 degrees in Portland, Oregon, 110 in Eugene, Oregon. 104 in Seattle, Washington, marking the first time the city passed triple digits 2 days in a row since record-keeping began in 1894.
Unfortunately, we're starting to see this year after year. It's getting hotter and hotter. Climate change is real.
Seattle's summer months are usually mild, with average June high temperatures in the 60s and 70s, so many homes don't have air conditioning. Now, stores selling portable units are having trouble keeping up with demand.
So those are the kind of things that people see. So people feel the event, but not typically they have difficulty to understand what's the meaning of indices. So it's much easier to communicate with general public with this event approach. And why do I come to this event view? It's basically before I'm working on this probabilistic extreme event attribution. So in this type of study, we just try to quantify the risk due to the human impact in the past, due to from the past or in the future. But typically, how do you make this attribution for the weather and climate event? The first step in this review paper by Otto et al., that you have to say what happened. And then the second step is you have to have a clear event definition. Okay, so you have to think about event instead of indices. Okay, but if you look at even this 2021 summer heat wave in North America, and look at, there are many papers on this. But if you look at all these papers, none of them define this event exactly the same way. The box they choose is somewhat different. Of course, they always choose the place where the temperature anomaly is larger, that's true. But when you try to quantify the return level to a certain precision, then those selection does matter. So I'm thinking about at the time that we probably should let the extreme events speak for themselves. So one of the earlier papers with my student in 2021, we are trying to say that how do we do that? So here is just an example showing in this European 2003 heat wave. And most of people know is the one in the Western Europe that occur in August. But if you're using this type of a technique, you can actually detect this earlier one in Northern Europe, okay? And to identify this, I will explain it more, but there's only two main things you need to do to depict a extreme event. One is that you have to find a threshold to say where these extreme occur or when this extreme occur, okay? So in terms of space and time that you have these places and time that extreme occur. Then the second step is also quite simple. So you would like to try to find a connection spatially or temporally with those boxes or places that are connected together. If they are connected together, they are the same event. If they are separate, they are different events. So that's the sort of a idea we can do. Then if you do that because you have this distinct fingerprint in space and time, so that you can also study the concurrent meteorological condition to lead to those events, or do a statistical like this one that we obviously see that in Northern Europe, what's the time for those extreme occur in terms of x-axis. And certainly the later one is longer. And also the area, which showing the vertical axis, the higher vertical axis, you can also see that the area on average is larger. And also this color means intensity, that the one in the Western Europe is much more intense compared to the early one. So you can clearly see many different attributes of a particular event using this approach. So first thing for the heat wave, you can do it on different extremes. For example, precipitation extreme, drought, wildfire, and so on. But first thing, because you have to define a threshold for the extreme to occur. So you have to find some intensity index that you can do. So the one for heat wave, we are not developing by ourselves, we are just using one of the popular one developed by Russell et al. 2015, that they have a daily magnitude for the heat wave. And the way they define is first that you have to set up this, what is the period for the heat wave, typically use A particular day, use a 31-day running window and take 30 years of data, and then any temperature that is higher than like 90% for consecutive 3 days. Those are the so-called traditional indices try to define the heat wave. Then this daily magnitude is just the daily temperature using that to contrast the 25 percentile of 30 years of annual maximum temperature. If your daily temperature higher than that, then you have some value. If lower than that, it's zero in terms of daily intensity. And it's measured by this interquartile or 25 to 75 percentile between or among this 30-year annual maxima. Because it's choosing the annual maxima, it only occurs in the summertime. So in the previous definition, usually warm spell can occur in the wintertime, but here by this definition, that you will only have this in the summertime. Of course, in the tropics, it's a little bit different because of this less of a seasonality there. But anyway, so we typically in this study use this occurrence threshold as this MD or daily magnitude to be exceed 1. So that it has to be larger than 75 percentile of 30 annual maximum temperature to be counted as a voxel or box. Then the second thing is I said that you have to have an algorithm to find the connection. So you can find from this many mathematical algorithms for this type of thing. The one that we use is so-called depth first search algorithm. So in this way, you can using algorithm to separate different event or group the same event. So it's simply like the one where people solve the puzzle, try to go out inference, okay? Or simple example is just that these are the places that exceed the threshold, but you can sort of take these two as a different event, okay?
So can I ask you?
Yes, sure.
So on the upper two figure, they are space in horizontal and time.
In vertical, yeah. In my study, the 3D voxel volume is always horizontal at a particular time and then go through time. I will explain more as to how these construct.
So the purpose
later.
is that we use the previous index inside each box. So you can decide that box is a
It's a place that you should take.
yeah, and then if all these boxes connect to each other either horizontally or vertically,
Yes.
they are considered one event.
Yes, if it's separate somehow.
And all these
Then-
green boxes in the left-hand side, based on your method, at the end will be
Two
defined
green.
as a two Heatwave event.
Yes,
Okay.
that's right. Okay, so that's the idea. So the data we're using is era 5 data that back to 1940. And the resolution of the data is actually up to quarter degree, but because later we are using the Siemens model anyway, so we remap them to the 2 by 2 degree resolution for detection and tracking. And since most of the heat wave is a larger scale, so this probably is not a problem. But if you are interested in extreme rainfall, then you probably would like to have a higher resolution for that. And the event criteria, I say that this connection horizontally has to be this occurrence or extreme occurrence has to be daily magnitude exceed 1. But temporarily only we set it 0.5 temporarily, simply because, well, you should have a more spatial coherence, but sometimes heat wave can sort of reduce max the in between, so you don't want to separate them too easily by raising this threshold too high. But anyway, you can define whatever you want. Then there's another thing you have to consider, because well, there could be a lot of single boxes and so on. There may not be that big in terms of impact. So what we start with is that the number of after the connection, the number of voxels as 3D as contrast to the pixel in horizontal. So at this 4, but the 4 is just means because we're using 2 degree by 2 degrees, just 2 degree by 2 degree area, that's for 4 days, for example. And I'm showing the one of the box in the Washington state to show exactly how large is the area. But that's the way we define. So here is just how do we do daily. So every day you can check your daily maxima where they occur, and then every day you have some of the information, and in the end, this so-called 3D, the vertical in terms of time, is just like the animation there. Okay, and the way we do that it's not on this it's not only that event perspective better linked to the disaster risk, loss and damage, and also try to communicate with this storyline approach. You can look at the concurrent interior condition and try to understand more about the driving physical process and so on, since you have the footprint. But also there are more attributes for this Heatwave extreme compared to the extreme index. For the extreme index, you still can do frequency, duration, intensity, typically like the EPA study. But usually those are based on single time series. They don't care about the neighboring condition in their way of calculation for the index. But for us, then this area or spatial extent is an important part of the event and describe the size that is matter for many different applications, if you like. And then you can also calculate the integrate total effect. For example, if it's a rainfall, the whole thing will just be how many volume of water going in. It's not just one day only. So you can think it the way that this integrate effect can be considered. And there are some metrics for these attributes. So one is this so-called Heatwave magnitude scale. That is simply the summation of the daily magnitude for all of these connected voxels of this 3D event object. So this is talking about the severity of this event in terms of a total effect. And then you can calculate only the volume, but not taking the intensity in. So just look at the spatial and time structure. And then you can calculate the duration by counting the first day to the end of day. And then if you divide it by 2, then you get the mean spatial area for that particular event. Then you can do the decomposition. And when you have a change, you can try to look whether they can use this fractional change to make a good explanation or not. Okay. And going back to this 2021 summer, actually this particular event occur in the early summer in that particular place. It's actually starting from late June to early July, and lasted probably only 10, 11 days. But even before that and after that, in the Western North America, there are also 2 of the events. Although if you look at this individual information, they are much smaller, and also you can use this diagram to see how the area, the intensity and duration change. The big one may not be lasting longer than the other one, but certainly the area and the intensity are much stronger in a sense, okay? And then, as I said, after you do that, apply to all this era 5 data set from 1940, and if I counted only this IPCC there are 6 North American region. There are 6 sub-region. If I make a summation total, there are about 2,000 events. Goes through this 84 years. And then again, as I said, the event criteria is just the same as before we described. And then on the right-hand side, here is this bubble chart of all of the events that I described. And then this mean area, effective area in the vertical, and the x-axis is duration, and the intensity showing the color, and the size is the integrated effect. And what you find, what I find interesting is actually this 2021 early summer heat wave in Northwest Pacific Northwest, sorry, is actually the number 1 among all of the heat wave occurring in U.S. Although there are actually 3 of the event last year, all listed in this top 5, but they are somewhat smaller than this 2021 cases. So here,
Question.
yes, right.
Can you go back to the prior slide? This phrase, MD greater than 1 spatial connection, MD greater than 1 electrical connection.
Right.
Can you explain again what that means?
That means when we do connection, we can say, well, first of all, is that you sort of identify every box with a certain threshold. And then when you do the connection, you can also argue whether the connection strength, the both sides has to reach 1. And in that case, horizontal, that both has to be reach 1 to be connected. If there's a 0.5, so there will be sort of separate between them instead of connect together. But if this 0.5 is occurring but in terms of time, they will be connected together. So
it's sort of like a break in time.
yeah, so as I try to explain that, yeah, during the heat wave, there sometimes has some reduction of the amplitude, but not necessarily that much. So you try to keep them as the same event instead of break them to.
Yeah.
Could I ask you
Yes.
a question? So in your 2021, you said parents is 1. What does 1 mean? I saw you say
1 is number 1.
number 1.
Yeah.
But that year, that event actually, in that Pacific Northwest, you have 3 events, right? Based on
There are 3 events, but the other 2 are way down.
and how did you decide who is number 1? Who is number? What
Yeah,
is
so
number
this
one?
is a magnitude scale that I
Okay.
define there. So you just accumulate all these daily magnitude for the whole volume, okay, or for whole 3D voxels or 3D object for all these voxels that you identify as extreme occur. Anyway, so this is top 10 that in the list. Then, as I said, you can go back to find this detail, and there are some of the cases actually occur in 1940 or 41 or 1954, which is, although early in the period, they can still have some of the event occurring in the early time. And then the second column is certainly this way we define this particular ranking, and it's sort of identify which area they occur. So some of them are this Northwest, North Pacific, and some of them in the Central North Pacific, and so on. But I cannot get some of the earlier pictures, but probably can get the era 5 data to look at the meteoric condition. So, okay, so going back to this time series, how this time series works, they are definitely significant in terms of a linear trend. Then if you compare 30-year period in earlier time and later in the time series, the increase from 15 to 31 is roughly 2.1 times more likely to have this event occur. And this is only about global warming between these two periods, only about 0.5 degree also. But this seems to be a lot of numbers. So as I said, that more than 4 voxel is the sort of linear criteria. Don't want to take too many cases out. But then you can do additional criteria. For example, if I look at only those events that has their magnitude scale or this total integrated effect that more than million square kilometer a day, because this 3D is horizontal area times time, then the number dropped to only about 3 to 4 per year for the whole North American region. But still, this linear trend is significant. And this, if I again take these two periods, one is about earlier period is about 2.2, the later 4.6 is again about 2.1 times more likely to occur for these extreme events. Okay. And this is whole area. If you look at the individual area and look at how they change, they can be less. For example, this Western North America, where this California located, it's actually somewhat smaller than the whole domain average, but still statistically significant. But on the other hand, if you look at the Central North Pacific, it's still increased, but it's not statistical significant, only increase about 1.2 times more likely. Okay, and if you look back to this station result, it's actually still showing probably similar thing that in this Central North Pacific region, this increase from those stations are indeed is smaller than other regions that I show here. And you can look at this ratio between the two from this particular North American whole area or the individual area. And what you will find is that some of this Northeast North American region, the ratio is higher. And also this, as I said, North Central American or the Western North American are somewhat larger than this area average. So that also imply those, and all of them are, if you take a linear trend, they are all 99% significant. But both of this Central North Pacific and even Eastern North Pacific is somewhat smaller. So there's a regional difference if you compare this sort of violin box plots between these two periods. Okay, and how about a detailed distribution? Okay, well, certainly we can also look at a detailed distribution like this. So again, this is the if I now separate them as 42-year period as to only sample 30 year, so that again this is sort of the change between two periods, and you can look at the differences that to find out where that increase more. And in additional to the genesis point, we can also look at this occurrence density, like typhoon tracking, so that the heat wave can last many days. So every day we can look at it as centrally, and then doing a calculation, determining the daily central location, and then you have a much more of a sampling there. Okay, but by and large, the pattern are quite similar to each other, since most of the heat wave are not moving that much. And if you look at the seasonal cycle, they are predominantly occurring in the summertime, and the ratio of increase in both June, July, and August are pretty much similar. But then the later period, you have a much more case even occur in May or in September. Okay, And this is additional attribute I would like to talk about. If you look at the total effect, the integrate effect, how much that in these two periods they change. So increase using this box varying plots like this, but the increase internal mean is about 135. Okay. And you can separate them, as I said, to volume and intensity. And so this, all the voxel number is increased, the majority of the increase is due to this voxel number change, increase about 121%. And although this magnitude, mean magnitude is also, increases only about 9% also, but it's still also 99% significant if you look at two distribution. Okay, so they are not contribute more, but they also significantly increase in the past. And you can further, as I said, decompose this volume into the area and duration, and about 60% is due to the mean area and increase, and about 51% is due to duration increase. Okay, that's sort of analysis you can do. Then you can also try to look at regional difference. And again, similarly, actually, if you look at the whole area and take each period, the top 100 for the whole area or the top 50 events for individual cases, since, well, here it's not intended by frequency, I want to compare the attributes. So I control this top numbers for the comparison. But again, this ratio of the increase of this total integrated effect is much more on this Western North America and North Central America, and also Northeast North America. And again, this two of the Central North America and the Eastern North America are somewhat smaller than the whole area average, although they are still increased by somewhat. No, they are actually decreasing in terms of a total scale. Okay, sorry. And you can also look at the area, similar regional difference. You can find duration actually also similar, although does not really differ that much by area average, except those Central and Eastern North America region. And the mean intensity also not changing that much among different regions, probably except some region are somewhat higher than the total domain average. Okay. Then the next part is go to using this CMAP data set, and these are the 24 CMAP model we're using that has this daily T maxima temperature that we use from this era 5, and we are looking at both historical period for those 30-year period I mentioned earlier, but I also look at the end of the century, 21st century, from this SP 585 scenario. Okay. So these are the so-called, if you want to do feature projection first, you usually take doing the validation. And in terms of validation, compared to the era 5, and here is 24 model ensemble mean, and these are each individual ensemble. So it's not that easy to make a comparison with even with this large sampling, because this 2.2 grid is still quite large numbers for the whole North America. But of course, if you have a larger sample, you have a more smooth pattern there as compared to the observation only one realization. But then we can look at more detail later. Okay, and this is the difference between the two. You can probably say that model are producing somewhat more event frequencies, especially the central North Pacific toward the south half. Okay, but each individual model are different. Okay, and then if this case, you can try to look at all of the different years from the model and from the era 5. And look at the mean tested, doing a statistical test for the mean, their standard deviation, media, or the trend, or even the distribution using Kolmogorov meal test for the distribution and so on. So you will find that only probably 1/3 model has a reasonable result, and there are many models actually is overproduced for this. Okay, but model certainly has some of a bias, even though this particular index are using percentile, which may reduce some of this requirement for the accuracy of the model projection. But how about, yeah, since there are many cases, so again, if I'm using this total effect of more than million kilometer square times day, only those cases. And then all this model online are much better than all cases, meaning that, yeah, if you are only interested in those most extreme one, so their mean value, their spray, and their median value, and so on, is good. Although the trend tend to be, if you only look at this 30-year trend, sometimes not really fair to this model, since they have their own natural variability. So, but anyway, in general, at least half of them, or more than half of them, is a higher linear trend. Okay? Otherwise, the distribution is fine. And then again, you can look at other attribute like mean area. It's again a lot of model, at least more than 2/3 are reasonably good compared to the era 5. And how about the duration? Duration tend to be much more than era 5 result if you look at these models. Okay, although they are not way off, especially if you look at the median value, which is less sensitive to outlier. And then how about mean intensity? It's not that far from the observation, although if you do a statistical test, it's probably only half of them can pass the statistical test because of the large spread, usually, okay? So in the end, if you look at the total integrate effect, there are still 2 models actually can probably still quite close to era 5, and all of others in terms of mean value is okay, but they tend to be has much more spread, especially for these large events producing in these models. So this is, if you want to check. And how about the future changes? This again, 24 individual model, and upper right here is the ensemble means. Okay, and then if you sort of compare the ensemble mean of the future changes, and here is the ensemble mean for the historical period and how it changed. Again, you will see that, of course, individual models are different, but ensemble mean tend to indicate certain area which is this event frequency increase much more than is true. And Western North America are one of the places which is somewhat less in terms of the increase. Okay. And this is going for the frequency density, similar result compared to the genesis only. And how about projected change in terms of other attributes? Okay, in terms of a ratio between the model end of century and present day, here's the spread of this ratio. So roughly all the model give you this range between 2.5 to 5.5, but majority is probably between 3 to 4 times more likely to occur, okay? And how about individual characteristic of the event? So actually, if you look at total integrated effect, it's actually increased 72 times as much, okay? This is a ratio. And if you take them, what's the contribution? Of course, this volume increase is the major contribution, although this magnitude increase in terms of ratio also reaching 2. Okay? And if you further separate that, more of the contribution here is actually from the duration compared to the mean area, although from historical data of era 5, we found that area is somewhat more important than duration change in terms of historical change. Okay. But these are the model projection. But model projection give you 72 time increase. What exactly happened? Okay. So that's the interesting part that I still, because these results are quite new, I try to making the analysis before I come here. But one thing you find is interesting, right? The low part is the one that I showed you before when you look at the model performance. They are in line with era 5, okay? But if you look at the future, in terms of mean area, you will find that strangely, you have because these are top 100 events I choose from each period. So actually, even for a top 100 event, you have many model producing that actually the top Heatwave event in the future, although it's total increase, in fact, increased by 72 times, but many models actually produce a smaller mean area for these events. See, so and a lot of them spreads downward instead of upward. Although there's 1 or 2 models actually only go upward. So there are quite different model behavior there that can be interesting. You know what's going on there. And if you look at duration, okay, again, this is the historical run that's reasonable, as I say, compared to the observation, although it tend to be too long, okay? And how about the future? Okay, here is the future. Look at the scale there, okay? So it's reaching 500 days. The reason of 500 days is because we are sort of initially detecting for a globe. So, you know, for every year, so we have to connect the end of year through the first 5 months to the next year so that the southern hemisphere can be detected at the same time. Okay, so because of the seasonality change. So because we allow this additional 5 months, it reached actually 500 days, which means pretty much every day is heat wave for those particular cases, although not a majority, but all of 100, top 100, but there are some that look like that. If you put in the same scale, that's the current day, it's just a tiny dot there. So all of them are just going up like crazy, okay? And again, why is that? So when you look at the area, when you have an area reduction, but actually time increase so much, so that even if you have a small region of a heat wave, because it lasts so long, so that in terms of the total effect, it can still be very large and put into the top 100. So here is a thing that we can try to figure out. And the mean intensity is also increased quite a bit, as you can expect, because of the warming from this SSP 585 cases. Okay. And then the total integrated effect is just shifting all upward, because it is compensation effect from the duration and the area are sort of cancel out for this model. But still, you can see some of the strange things here, okay? So finally, I want to give two examples. These are kind of strange things. So what happened exactly? So if I pick up one more models, this French model, that take the number one case in the present climate, showing the lower left here, that occurred in this model year of 2007. And I'm asking how many cases that is larger than this number one in the historical, which means that just if it occur in the future, they are going to be unprecedented compared to the present case. And these are the distribution. Again, I'm using the same bubble chart. In the mean area, event duration, magnitude is color, and the size here is the negative effect. As I say that why there's even 100 times larger is simply because it's a tiny one, although the intensity is weak. But you have some cases that the duration may not be increased that much, but the area increased quite a bit. But you also have this sum of a thing, that area are not that large, but the duration increased a lot. And these give you, and also there are some of the cases, a smaller area, but lasting quite a bit long time compared to before, but has the intensity much more than current. So you can think about how the heat wave in the future will change compared to the current, the most severe heat wave we know, and how future will go to. And you can think about what happened there in this North American region. I have some guessing, but maybe leave you to think about this. And how about this particular, those are one model that has this strange behavior. But if I choosing this particular model, which is GFDLE Earth System Model 4, which does not have this extension downward for a smaller area cases, okay? So here is this particular model project for future cases. There are actually 39 cases that are higher than the top one in the current history that occurred in 2012 in that particular model, and showing is tiny here, but you can have a large increase of area and large increase of this duration, although this duration are not going to last that long, go through a year. But that typically related to this North Central Pacific area, which is toward the tropics. And the tropics, although still have this increase of temperature, although smaller than high latitude usually because of this polar amplification effect. But actually the noise level for the tropics is even smaller. So when people talking about the emergence time is actually much early for those tropical regions, and this is sort of showing up here for those large cases. Actually, when you have this long duration, then typically you get this type of change in the future. Okay, so I will conclude here. So as I said, the frequency of heat wave increased significantly in the North America since 1940, and the Central and Eastern North American experience somewhat less compared to the mean. And if you look at the top event of this early summer to 2021 case, the size is about 40 million kilometers square a day, and the reason for that is just that they have this unprecedented mean spatial extent reaching almost 2 million kilometers square, which is about 1/4 of a continuous USA for the size, and an unprecedented mean intensity of 2.1 compared to before. Okay, and this event actually are more than double of any historical event, and about 20 times larger than mean severity of all of the events over the same region. Okay? And as I said, you can look at an individual attribute and try to look at the contribution of each one. And these also has a regional difference similar to frequency changes. And for the model projection, that model, although if you are using the same threshold, seems not similar that well. But if you are only look at those more extreme cases, as I said, that the wrong number there, but more than 1 million, and then it's more properly simulated in terms of these senior models. And the future projection, as I said, can increase by 3 to 4 point times. But if you look at the individual attribute, as I said, the integrated effect can be increased from 30 to 270 times for the whole North American, for durations 4 to 20 times, mean area about 2 to 4 times, and the magnitude increase is about 20 to 100% increase. Okay. And why there's such a large difference between this climate change in terms of these individual heatwave attributes? I think it also depends strongly on the model climate sensitivity, since some models get warmer than others, and also the warming pattern are different. And then the internal variability of an annual T maxima that can be also play some role there that I would be interested in. So I'd say that from an event perspective, it can provide much more information and better storyline communication to the general public. And when you get a detailed evolutionary characteristic, those are not be able to be captured by the industry study. And the final part I try to, as I said, I try to promote my methodology that, as I said, that it's not really limited to the heat wave, or even the heat wave, we can use other index. There are other index for the heat waves as well, and try to see how much the change of the drought also has a lot of index, or wildfire index, flooding, heavy rainfall, and so on. And you can apply to not only the model, observation, and feature projection, although some caveat there, and also doing attribution if you want. And you can do actually a compound event, because when we do this individual extreme individually, but when they have a joint in terms of their footprint, that the compound event occur. And for example, drought, heat wave, wildfire are typically joined together. Cold surge and strong wind are typically a compound, or the heavy rainfall, flooding, and landslide. And you can also extend it to the impact study with population data, vulnerability data, or loss damage data. And it's better use this to study the physical mechanism and direct link to the weather system that drive this change in the extremes. Yeah, start here. Thank you.
So let me ask the first question. So in the historical data, you have 30-year period, right? So
yeah, when compared with model, because...
No, I mean not just in observation. So you say
yeah, okay.
30 years, the increase of heat wave, mostly because heat wave got longer duration, I do the attribution. As well as the volume got the trend, right?
Yeah, but the observation, the volume increase about 120.
And most of the increase in volume is due to the duration increase.
No, for the observation,
yes,
it's like 60 to 51. So roughly the same contribution. But in terms of a future projected change, the duration increase is much more.
Much more. Okay.
But the reason for duration increase pretty much due to this North Central America, which is more toward tropics, where you have a small noise level or the internal variability, which are important for those for those daily magnitude calculation. When you have the temperature higher than like 3-4 degree, then the whole period can be as large. Yeah.
Comment, please.
Yeah.
Thanks for that interesting talk. So I had two questions about the voxel tracking method for the
Okay.
event detection. So the first one is, I didn't quite understand why there was the limit of 500 days. So is it that you're analyzing the data in 500-day chunks, and 500 days includes the year plus a little bit on both sides?
It should say that when my students do it, they do it each year by each year, not continuously, because try to save some of the memory that needed for the detection and tracking. So if you do the annually, then southern hemisphere has the summertime, the other one, so we sort of try to extend that. But we make sure that once it's been detected before, so they were messing out, won't be participating with the next year's tracking. Yeah, so.
But for the data where it's 500 days, it's possible that that actually just spills into much longer than 500 days.
Yeah, could be.
Permanent.
Yeah, should be actually, because it's like starting from 2 to 560. Yeah, so pretty much whole period.
Okay,
That's
so
true.
related to that, I had a question about the scalability of these methods. So we have an ocean model data set where I want to do this voxel tracking, but the data set is 10,000 times bigger. And I just
The number of the grid.
well, the size of the grid and the time, it's 600 years of simulation.
Yeah.
And so when we tried putting the data into some solver that tried to count all these events, it just crashed. So is there a way forward for these big data?
But as I said, one thing is that if you're not doing it continuously, that's certain self that, but later on you can still, within a year that you, unless you really last several years, then that's a problem. Otherwise, if it's only this seasonality problem, that's probably easier to solve, I think. And the other thing is that I will always test different resolution of data. As I said, that if you really have this problem of memory size for your particular algorithm, and you cannot really optimize the efficiency of using it, then you use a coarse resolution data to test how much different you get from this coarse resolution compared to high resolution, and make sure that they are not really sensitive to the resolution. And that I do with the rainfall data, for example. Although because we are starting extreme rainfall, we like to have those very high resolution, like 5 kilo grid resolution for the large region. But then again, I will encounter the problem if it's too large. Similar problem to you. Then always things I would test is try to reduce it a bit and try to see whether the statistical event are pretty much the same, and so that I should be fine. Although I lose some of the extreme intensity, but unless you can find a better way to do the tracking, otherwise that's one of the solutions you can try.
Yeah, please.
Thanks, this is really interesting, and I'm going to come talk to you more after, because I do a lot of work on heat waves, and we should have met, and I screwed up with my email. But anyway, to ask one question, I think the idea of heat wave genesis locations is really interesting. Like, I know people think a lot about that with tropical cyclones. Heat waves, they're like a different beast than tropical cyclones, but what have you learned from looking at these maps as heat wave genesis? Like, do you think that's a interesting direction to explore further, that we can learn something more about the processes of heat waves, or is it are they like so fundamentally different that something like a tropical cyclone that there's sort of a limit to what we can learn from that perspective?
I haven't think about that much since those spatial distribution does need additional care, I think, in order to really understand why. Yeah, so, but as I said, we do have this occurrence time so that we can really check them with the condition that leads to those occurrence. But that, of course, when you have 100 or even 1,000 cases, it still takes a lot of work for us to know each individual one. So, but it's of course doable. It just takes a lot of work to do. So if you have develop a good strategy to streamline it more efficiently by looking at that. Because the Era 5 does this all of this conjunction condition that we can double check. Yeah. So I would think yes. Especially Heatwave, when we look at global, that can have a very different mechanism there. Because from Taiwan, for Taiwan, we typically associate with subtropical high location.
Right.
It's nothing to do with omega blocking. And as I said, for India, which is another story where the heatwave always occur before monsoon, so the precipitation, the occurrence of the precipitation condition is very important for those areas to produce heat wave. So the reason can be very different. The Brazil is typically also associated with drought also. They can be very large. So things can be complicated when you look at all of these regional differences. But I will imagine that in North America, that most of them should be similar. If I look at this Western, Central, and Eastern region, not look at the further south, I look at the further north. Or further north is probably fine. But the further north is some problem when we look at the future projection when the temperature increase quite large. Then some of the results look weird, although can explain about why is that.
Thank you very much for your talk. I just want to find out those open heat islands have any effect on the intensities of the increase.
What island?
Open heat island regions.
Urban heat islands.
Oh, urban, sorry, yeah, didn't capture it, okay. Yeah, well, if it's occurring in the Era 5 data set, so you're asking whether Era 5 show the urban heating signal in the reanalysis data. If they are, then they should. They are not really doing that much in terms of data assimilation. I don't think the model has this building of this surface condition that lead to urban effect in the European Center model, although I'm not an expert on those reanalysis data. So we should think about on those lines to see whether that play a role.
Okay, thanks, Professor Chen.